display the changes in the output state until the clock pulse becomes 0 is by the use of the master-slave flip-flops. Here we see a simple master-slave RS flip-flop. It contains two clock RS flip-flops and a logic inverter. The master-slave flip-flop will be contained in a single IC package. The operation of the master-slave flip-flop is very simple. For example, we will assume that the master flip-flop had previously stored a high at Q when the clock input is 0 or low. The clock input on the master flip-flop will be low and the clock input on the slave flip-flop will be high. This is due to the inverter in the circuit. This causes the output state of the master flip-flop to be forced into the inputs of the slave flip-flop. When the clock input becomes high, or 1, then the clock input on the master flip-flop will become high, and the clock input on the slave input will become low. This causes the inputs on the slave flip-flop to become ineffective. Therefore, the slave flip-flop will store its previous information, even if the master flip-flop changes its state more than once while the clock input is high. As you can see, the master-slave flip-flop is very effective in maintaining its information from one clock pulse to the next. Master-slave flip-flops are available in all flip-flop configurations. In the various flip-flops shown thus far, the control inputs are effective during the interval that starts at the leading edge of each clock pulse and ends at the trailing edge of the clock pulse. However, there are times when the inputs must only be effective for a short interval of the clock pulse duration. In such a situation, the edge-triggered flip-flop satisfies this need. In the positive edge-triggered flip-flop, the control input is sensitive for a short interval of time near the positive going transition of the clock pulse. The outputs of the flip-flop change shortly after this interval. In the negative edge-triggered flip-flop, the control input is sensitive for a short period of time near the negative going transition of the clock pulse. As before, the outputs of the flip-flop change shortly after this interval of time. Note that the symbol for the negative edge-triggered flip-flop shows an inverter operation at the input of the clock signal. Here we see the JK flip-flop. It is the most versatile of the flip-flop configurations. Notice that the JK flip-flop has 5 inputs. These are the J, K, preset, clear, and clock. The preset and clear inputs perform the same function as the set and reset inputs of the flip-flops previously discussed, except these inputs operate with the clock pulse held low. Notice the inverters placed on the IC. Also notice that a function table is given with the flip-flop symbol. Let's take a moment to examine this function table. When both inputs J and K are low, the flip-flop will remember its present state and the outputs will not change with the next clock pulse. Now suppose input J remains low and input K swings high. The flip-flop is then instructed to reset output Q to a low state on the next clock pulse and set not Q to a high. If on the other hand input J is made high and input K is made low, the flip-flop is instructed to set output Q high and output not Q low. And if both J and K have a high input, the output will toggle from one state to the next with each clock pulse. JK flip-flops may be found in digital circuits used for control, as registers, or as a toggle function. JK flip-flops are also available in edge-triggered devices. Notice that the negative edge-triggered JK flip-flop has an inverter at the clock input. The flip-flop is a digital circuit with two outputs which are labeled Q and not Q. The outputs of the flip-flop are usually opposite. In this video, you have examined the RS, D, master-slave, edge-triggered, and JK flip-flops. Master-slave flip-flops are used to latch an output to one state or the other while the clock pulse is high. Edge-triggered flip-flops are used when the inputs must only be sensitive during a small portion of the clock signal. Both positive edge-triggered and negative edge-triggered flip-flops are available. The JK flip-flop is the most versatile of the flip-flop configurations. Its uniqueness is in its ability to toggle from one state to the other when both inputs are high. This concludes review number 2. The set input of a flip-flop is sometimes called the preset input, and the reset input is sometimes called the clear input. Next, we will examine the D flip-flop. The D stands for data. If you will look closely, you will see this flip-flop has 2 additional inputs. One is labeled D and the other is labeled C. D is for data input and C is for clock input. You will find, however, that some D flip-flops will not have the set and reset inputs. They were mentioned so you know they are available. To better understand the D flip-flop, we will examine its equivalent circuit. Notice that this circuit consists of 2 NAND gates, 2 NOR gates, and 1 inverter. We also have a clock input, a data input, and 2 outputs, Q and not Q. The clock input is a recurring signal that initiates the transitions of the flip-flop. When the data input is high and the clock input swings high, it places 2 highs at the input of NAND gate A and a high and a low at the inputs of NAND gate B. Notice the high was switched by the inverter at the input of gate B. Since gate A is a NAND gate and it has 2 highs at its inputs, we know that it will produce a low at its output. Also, since gate B is a NAND gate and it is receiving a high and a low, it will produce a high at its output. As you might recall, when a NOR gate has any of its inputs high, it will produce a low output. Therefore, NOR gate D will produce a low output, which is fed into NOT Q and into the second input of NOR gate C. At this point, NOR gate C has a low being applied at both of its inputs. Therefore, this NOR gate will produce a high at its output. Notice that the information which was present at the data input has now been switched to the Q output. Now suppose we make the data input low and apply the high clock signal. As you can see, gate A has a high and low signal being applied, and gate B has 2 high signals being applied at its inputs. The low and high condition of gate A will cause it to produce a high output. Gate B, on the other hand, now has 2 highs being applied at its inputs. This causes this gate to produce a low output. The high signal from gate A is fed into gate C. This high signal at gate C will cause it to produce a low output. The low output from gate C is applied at the Q output of the flip-flop and the second input of gate D. The low signal from gate B is fed directly into one input of gate D. Since gate D now has 2 low inputs, it will produce a high output. Therefore, output not Q will become high. By now you should have noticed that the output at Q will be the same at the data input when the clock signal is applied. As we mentioned earlier, some D flip-flops also have set and reset inputs. However, on most flip-flops, the 2 inputs are labeled preset for set and clear for reset. When the preset and clear inputs are at logic 0, they have no influence on the operation of the flip-flop. However, when the preset is made a logic 1 and the clear input is at logic 0, the flip-flop will set to its 1 or high state regardless of the control inputs and the clock. In the same respect, when the clear input is at logic 1 and the preset is at logic 0, the flip-flop will set to its 0 or low state regardless of the inputs at the data and clock. If, on the other hand, both of the preset and clear inputs are made high simultaneously, the output will result in an undetermined state. It could be high or low. Here we see a quad-type D flip-flop. This IC can be connected as shift registers or counter elements, as well as for specialized switching and timing control circuits. Even though this IC contains only 4 flip-flops with a common clock and reset inputs, there are other ICs available which will contain up to 16 flip-flops. As was just mentioned, the 4D flip-flops are controlled by a common clock and reset signal. You may also have noticed that the data inputs D0 through D3 to each flip-flop, as well as the outputs for Q and not Q, are buffered by separate amplifiers. Only during the time that the clock signal swings positive will the data which is present at the D inputs be transferred to the Q outputs. The reset function, however, is possible at any time and is independent of the clock signal. In the Type D flip-flop circuit shown thus far, the data input was not allowed to change while the clock input was high. This ensured that the flip-flop was left in a definite state after each clock pulse ended. If the input information changed while the clock pulse was high, the output at Q would change correspondingly. This would cause no problem so long as the flip-flop was used only for the storage of digital information. However, the flip-flop is used for other applications where this change of state could create false information. In such applications as counters and shift registers, the change of state at the output must be delayed until the inputs are no longer sensitive to change.